Cool. Okay, so I thought today what we'd do is follow up the discussion we had about differential entropy by computing it for for a few example distributions. So one of these is actually one of the end of chapter problems. So I thought instead of just doing it for the Gaussian, which is the one that's there, we'll do it for that and a couple of actually simpler distributions as well, so you can see how it's computed and also get a feel for how it works and how the parameters of the distribution play into it. So let's just recall what the definition of differential entropy was, and it was very similar to the definition for the entropy of discrete distribution. So if we have some some probability distribution p of x, then we would write h of p is equal to minus p of x log px. Another way you can write this is equivalently as p of x log 1 over p of x, it's all dx. And remember that we called, so let me just change colors here. So remember we called this the surprise. So this was, average surprise. Because we're taking the surprise here and we are taking its average with this p of x that we're given. And sometimes, and actually in the book, he'll often just write this instead of h of p. He might write this also as h of. He might write this equivalently as h of x, and that just means you have to kind of implicitly realize that he means the entropy of the random variable x, which has a probability distribution p. But actually, h is actually a function of p rather than x itself. Okay, so let's try computing this for a few distributions. So maybe the simplest one we can start with is the uniform distribution. So let's do that. So the uniform, and that's the one which has the same probability over its domain. So for example, that's why it's called uniform. So let's just take an example here. And we're going to have this, let's say this is x is equal to 0, and now we're going to have it extend all the way out to x is equal to L. And so now we need the probability to be uniform over that interval and to integrate to 1. So therefore, it's pretty easy to see that this probability, so p of x, has to equal 1 over L, because that way it will integrate to 1 over this interval. Okay, and so now we're interested. So here we go p of x is equal to 1 over L for x belongs to 0L and 0 otherwise. You guys can see that? Terrific. Okay, good. So now we can go ahead and compute this entropy here, but let's just think about how we expect it to behave. So entropy should be, it's a measure of our uncertainty. So we should expect that the larger that, and let me actually move this out of the way. So the larger L is, so the wider the range of values that x could come from, the larger the entropy. So we should expect that h of p should be kind of proportional to L somehow. So the higher L is, the higher the entropy should be, because it just means more uncertainty. So let's go and try that out and see if it's indeed the case. So it's going to equal to, remember, minus p of x times log of p of x dx. And our domain was going from 0 to L. And we have just said we've got the expression up there that p of x is 1 over L. So it's just going to, it's going to be 0L times 1 over L times log of 1 over L dx. And now we've got this minus sign, so we can actually apply the minus sign to the log. So we'll just get this to be equal to 0 over L times 1 over L log of L dx. And now you'll notice that none of the terms in the integral actually involve x, so we can just take them to the outside. So that's going to equal to 1 over L log L dx. And so then that's just going to be oops. So 1 over L times the log of L, so this is going to be in its own box, times L. And now this will cancel out this, and we arrive at our final expression that the differential entropy, so this is H of P, is equal to log of L. And that kind of makes sense. So first of all, notice that it's proportional, it's monotonic in L, so the larger L is, the bigger this gets. So that makes sense. It has a nice symmetry with the situation. Do you remember with the discrete distribution, when we had m possibilities that were all equally likely, the entropy there was log of m. So here you see it's exactly the same. The only thing to point out is that differential entropy can be negative. So if L is less than 1, this entropy is actually going to become negative. It's going to can be made arbitrarily negative. So it's unlike the discrete entropy, which is always positive or 0. The differential entropy can be negative, and we can see that in a simple case here. Okay, so that was one simple example for the uniform distribution. So now let's try another one. So let's go to the next page, and let me make a line here so I make sure you can see everything. Let's try another distribution. So let's try the exponential distribution. Okay, and what does this look like? So P of x is going to have one parameter, and that parameter is its kind of, its constant, its length constant, or its time constant if x is time for you. So it's going to be minus x over tau. And what does it look like? So it looks like this. So it's decaying. So it goes from 0 to infinity for, let's just say for, I'll say it up here. So for x greater than or equal to 0 and equals 0 otherwise. So it's, let's say this is our 0, x, all the way going to infinity, and we've got P of x up here. Now at x is equal to 0, we've got it sitting at 1 over tau, and its length constant, so that the intervals of x by which it falls to 1 over e of its value are tau. So we kind of measure these in units of tau, 2 tau, etc. So if you guys are familiar with electronics, that's kind of how long it takes a RC circuit to discharge, things like this. But we don't care about that. So right now it's just we have this distribution parameterized in a particular way, and we want to know what its entropy is. Now again, if we make tau larger, so if we make tau larger, then this distribution kind of starts getting wider and kind of wider. So this is, let's say, for increasing tau. So again, we would expect this entropy to be somehow proportional to tau. So let's see how it actually works out. Okay, so again, we've got h of p is equal to minus p of x. I'm just going to go from 0. This time it's going to go all the way from infinity because the distribution is defined over that whole range of log p of x. So let's plug in, and we'll actually plug in the log p of x first before we do the whole thing, because some things will simplify that way. It'll keep it less cluttered. So what's log p of x? So we've got log of 1 over tau times x of minus x over tau d of x. Okay, so let's continue. So that's going to equal minus, so we're going to expand the logarithm. So log 1 over tau, I'll just do it in 2 parts, minus, again, 0 infinity, p of x log of x minus x over tau dx. Okay, so we've got these 2 parts. Let me move them a little bit over because we don't need all this space. Okay, and now let's just try to solve them one part at a time. So with this first part, you can see that this log of 1 over t, it doesn't depend on x. So we can just move it to the outside. So I'll just do that part first. So let's just say it's equal to log 1 over tau times 0 infinity p of x dx, and there should be a minus sign. And now this, well, it's a probability distribution, so it'll just become 1. So we end up with just, this part is just going to be minus log of 1 over t, which we can just write as log of tau. So that's already good. That looks like what we were expecting at the beginning. We want this kind of dependence, this increase with tau. The larger tau gets, the larger log t gets. Therefore, that contribution to entropy increases. So that's good. Now, what about this part? So this second part is going to be, so the log of x of minus x over t just becomes minus x over t. And the minus and this minus cancels out. So we're going to get 0 to infinity of p of x times x over tau dx. So we can take the 1 over tau on the outside. So this is going to be 1 over tau, 0 infinity, p of x dx. Now this is just 1 over tau times the mean of the exponential distribution, which is actually tau. So this whole thing just becomes 1. And when we add these two pieces, we get that. So, we conclude that h of p is going to equal to 1 plus log tau. So, as we expected, as we already mentioned, the entropy will increase with tau as we expected. So that's good, but again, it can get arbitrarily negative. If tau becomes kind of very small, then h of p becomes small. So it's just always keep in mind. So if you're doing a calculation and your entropy is becoming negative, it doesn't necessarily mean that you've done it wrong. Good. So that was for the exponential distribution. And then finally, we'll come to the exercises in the book, which is doing it for the Gaussian. Now, the Gaussian is interesting because it has 2 parameters. So let's just see how that works. So there we go. So that's going to be our divider. Okay, so let's try the Gaussian distribution. This is the one-dimensional Gaussian. Okay, so here it is. You should memorize the formula if you haven't. You will by the time you'll have memorized it by the time you're done with this book. That's for sure. Okay, so what does this look like? I'm sure you're probably all aware. So let's put, this is our 0 point. This is x, p of x. So this is just a bell curve. So let's say this is x equals mu over here. And there's my bell curve, and this is 2 sigma. So the standard deviation is sigma. So a couple of things that we might need. We might need the fact that the variance of the Gaussian distribution is going to equal to sigma squared. So that's something we need, just like we needed before. The mean of the exponential was tau. Now we know the variance of the distribution is sigma squared. So we'll probably need that as we go. Now there's a couple of things. So before we before we compute it, let's try to think about how we expect it to depend on the parameters. Now, it's just like we were talking about before with the uniform distribution, where as L got larger, our uncertainty got bigger, and we would expect the entropy to increase, and it did. Or with the exponential distribution, where as tau got larger, the distribution became broader, and we expected the entropy to increase, and it did. That scale parameter is going to be the variance. So I think it's natural to think that this distribution, this entropy, is going to increase the larger sigma squared is. But now the question is, if we have 2 parameters, so what about the mean parameter? So should the mean parameter play any role in this? And I think that's that can be kind of a bit of a tougher one to think about, because you can imagine, like, if these things, when I was thinking about it, I was like, well, imagine if they have units, right? So suppose your standard deviation was, let's say these things were, your standard deviation was, I don't know, it was like one meter, and your mean was a meter. So now you would have your distribution is 1 meter plus minus a meter, and that seems like, oh, that's kind of a lot of uncertainty. But now, what if your mean became a kilometer, and your standard deviation was the same? So you would think that's actually a lot less uncertainty. That's actually quite tight. So maybe what matters is the distribution of your standard, the relation between the standard deviation and the mean. But as it turns out, things only depend on the standard deviation. And the way I think about that is to just remember back to how we derived this. So the differential entropy came from us quantizing the discrete entropy. And for the discrete entropy, you're just talking about symbols. So there's no notion of, oh, well, this particular value is so and so relative to some mean parameter that's somehow specified. It's just there's a symbol, and that symbol corresponds to the value, this particular value. And if you shift it by some mean, there's almost like you're kind of adding some like metadata to it, saying that, okay, well, it's still essentially the same symbol, but now you've added a header to it saying that the mean is a kilometer. But actually the distribution of symbols that you receive on your end as a receiver basically are going to be unchanged, right? So it's going to be, okay, so now maybe it's 1 kilometer plus a meter, but forget the kilometer, like there's no meaning to it. It's just this value relative, to the mean is now going to arrive at with the same distribution. The fact that the mean is now a kilometer or a light year doesn't really matter. What matters is the width of the distribution, kind of the number of different kinds of symbols you're going to receive, and the frequency with which you receive them. So I think it kind of ties into the fact that entropy itself, this notion it's kind of divorced from kind of semantic, it's divorced from meaning. It's just all about symbols and how frequently the distribution on those symbols. So maybe that helps you think about, that can help you think about the roles that the various parameters should play. So it will turn out that all that matters is the standard deviation. So let's go and have a look at that. Okay, so again, as before, for the third time, so the differential entropy is see, done it 3 times, I messed it up. Okay, so what's the domain of the Gaussian distribution? Well, it goes from -infinity to infinity of p of x log p of x. And just like before, I'm going to keep this p of x around because and expand the log p of x first, because that'll make our life easier. So let's just go over down here. So it's going to equal to minus p of x. So it's going to be log of 1 over root 2 pi sigma squared exp minus x minus mu squared over 2 sigma squared dx. So now, just like we did with the exponential, we're going to expand the logarithm. So that's going to equal to minus infinity p of x times log of 1 over root 2 pi sigma squared dx. So that's the constant component, minus the same thing, so p of x, and it's going to be log of exp minus x minus mu squared over 2 sigma squared dx. Okay, yeah, so now let's see what this becomes. Now again, notice that this constant component, it doesn't depend on x, so we can move it outside of the logarithm, and we've already done this once, so I'm just going to jump to the answer right away. And so this bit is just going to equal to log of root 2 pi sigma squared. And the reason why it's root 2 pi sigma squared, why it's come up to the numerator, is because of the minus sign. So that was the contribution from there. This little bit, so this next bit is going to equal to minus p of x. So the log and the exponential cancel out, and so we just get and the minus and that minus cancel out. So let's get rid of that, make it a plus of x minus mu squared over 2 sigma squared dx. So now the 1 over 2 sigma squared comes out, so it's just going to equal to 1 over 2 sigma squared times this. And what is that? That's just the variance. So this is going to be the variance of our distribution, which is sigma squared. So this whole bit is going to come out to being 1 over 2. So now when we add the 2 components, we're going to get that h of p is going to equal to the log of root 2 pi sigma squared plus 1/2. And just to make things a little bit more symmetric, we'll realize that this is 2 pi sigma squared to the power of 1/2, and we'll just take that outside of the logarithm. So it'll end up being 1/2 of 1 plus log of 2 pi sigma squared. Okay, so again, there's our dependence on sigma squared. There's no dependence on the mean for reasons that I hopefully help clarify for you. Again, it can become negative. And yeah, so that's basically how you do it. It's always good to just think about what you think the answer is going to be, or at least how. I mean, I didn't know the answers for these cases. I had to actually work them out, but at least we could think about what we expect the dependencies to be, what the nature of the dependency should be, and that's often enough to kind of catch any mistakes that you've made. And in this case, at least for the first few distributions, we kind of, there was only one parameter, and we could kind of guess the way that behaved. For the third one, there was two parameters, and we had to think a little bit, and it wasn't exactly clear, and so we actually had to work it out. And we saw that indeed the differential entropy of the Gaussian is increases with the variance as we expected. So hopefully that helped you do some of these computations. Are pretty straightforward, and it should kind of give you a better feel for differential entropy. So I hope you found the video useful. If you did, please give it a like, and I will see you in the next one. Thank you.